we are dealing with the numerical for isolated footing, eh, and we were at the point where we are calculating the depth from two-way shear consideration. Okay, so I will write that. So depth calculation, depth from two-way shear this is also called as punching shear consideration. Okay, now we are going to calculate the depth by punching shear consideration. Okay, so now for that I will write, for two-way shear, as we have discussed, our critical section is at a distance of d by 2. Okay. So I will write here, critical section is at a distance of d by 2 from where it is d by 2, from face of column, face of column. So now we will draw the diagram. See, now this is our column, this is the column. What are the dimensions of the column? The dimensions of the column are 0.5 by 0.5. So this is 0.5 meter. This is also 0.5 meter. 500 by 500 is our column. Now the next line is critical section. So this is the critical section. And now we will draw the footing. And footing is somewhere here. This is our footing. Okay. Now the diagram might not be accurate, but you can understand. So now if you see the critical section, it is at a distance of d by 2. So this distance, this is d by 2, this is also d by 2, on upward side it is also d by 2, and here it is also d by 2. So if I write over here now, so this is d by 2, this is also d by 2. Okay, so now see, this column will try to penetrate through the footing. This column will try to penetrate through this footing, and it will not alone penetrate, it will take the area about this pink rectangle with with itself, and then it tries to penetrate with this whole area. That is what is the concept. Then it tries to penetrate with this whole area. Okay, so now the next thing is, we will calculate the permissible shear stress first, then we calculate what is the nominal shear stress. You know two things. Okay, see, I will write here tau v. What is the meaning of tau v? Tau v is the nominal shear stress. Nominal shear stress. What is the meaning of nominal shear stress? Nominal shear stress means the shear stress which is actually developed over here, that is called as nominal shear stress. Okay, the shear stress which is actually developed here due to the loading is called as nominal shear stress. And the second thing is tau c. Tau c is nothing but this is your permissible shear stress. Some permissible allowable values are given by the IS 456 2000. Okay, so your nominal shear stress should be always less than or equal to your permissible shear stress. Due to the loading, now suppose now in the problem it is given that the loading of column is 1500 kilonewton. Now let us suppose one value. Suppose now this tau v which is developed over here, it is 100 newton per mm square. Okay, just for example take the value, and according to the IS code the permissible shear stress is 125 newton per mm square. Then this is okay, the condition is satisfied over here. Okay, but the reverse case is there. Suppose now nominal shear stress is 125 and the permissible shear stress is 100, then in that case this footing will definitely fail. Okay, so what is the condition we are getting? Our nominal shear stress must be less than or equal to permissible shear stress. So to find out the maximum value of depth, we can equate our nominal shear stress to permissible shear stress. Okay, our nominal shear stress to permissible shear stress. So now what we are going to do, see here. Okay, I will erase this first. So this is what the concept which I have told you right now. See, so here I will write, we know that, okay, we know that our nominal shear stress tau v must be always less than or equal to tau c. Okay, but it should be less than not only tau c, it should be less than ks into tau c, where where ks is equal to constant and its maximum value and its maximum value is 1. What is the maximum value of ks? Maximum value is 1. So if we consider the maximum value, then this ks become 1. Okay, so we can directly write tau v is less than or equal to tau c. This is our condition. Okay, you note down these points. These are the very important points. Okay, so now how to calculate this permissible shear stress first? So the formula for permissible shear stress is tau c is equal to, it is 0.25 under root fck. This is the formula, 0.25 under root fck. So if you put the values, it is 0.25 into under root 20. So now solve this and let me know the answer. What is the answer? Don't take too much time. Please be quick. So this value is 1.118 Newton per mm square. Why it is in Newton per mm square? Because this FCK value 20 we have taken in Newton per mm square. So this value we got in Newton per mm square. So now if we convert this into kilonewton per meter square, then what we will get here? Tau c is 1.118 Newton per mm square. So if we convert it into kilonewton per meter square, it will be 1118 kilonewton per meter square. Now these are the simple unit conversions. I hope now you are B students, so you are clear with this unit conversion. Okay. So now after this, see here, this distance. Now if you measure this distance, this much, and then this distance, how much it is now? So if you see, so to calculate this much of distance, so this is 0.5, this is 0.5, on this side it is d by 2, on this side it is also d by 2. So this total length is 0.5 plus d by 2 plus d by 2. So it will be 0.5 plus d. So I will write here 0.5 plus d. Okay. Similarly, if you see on this side, it is also 0.5 plus d. 0.5 plus d. Okay. So this is the dimension. Now I will tell you the important note where we are going to calculate the shear force. So I will draw another diagram. Now this diagram I am drawing for your understanding. There is no need to draw this diagram in the examination. Okay, so this is our column. Then after that, This is the critical section. This is the critical section, and then this is your footing. This is the footing. Okay. So now see, if this column, now if this column penetrates through the footing, if this column totally penetrates through the footing, then what will happen? The column will penetrate through this much area, whatever I have shown in yellow over here. So this much area will get deducted from this footing. Okay. So what area will remain? So the remained area will be, this area will remain. Okay. So the remaining area I will show here. This is your remaining area. This area will remain as it is. Okay. Whatever I am showing by hatching, this area will remain as it is. Okay. And the area which is not hatched, that area will get penetrate through the footing. So I will, for your understanding, I will give name to this. I will give name to this. This is the area. Okay. So this is nothing but area. Which area? Area which remains, area which remains after after punching action, after punching action. So this area is remain after punching action, and this is the area, this is the same area on which SF, that is shear force VU, is calculated, because this area will remain. हा तर एरिया तुमचा निघून जाणार आहे. Okay, this area will get punched, so this is the remaining area, so we will calculate the shear force on remaining area. So I will write here, so shear force is equal to stress or pressure. It is the stress due to soil or soil pressure, that is stress into area. The basic formula, force is nothing but stress into area. The simple formula we have written over here. So the notation for shear force is VU, which is equal to our soil pressure. The stress is sigma. That notation we have used, into whatever area we have shown here, that is hatched area. That area we need to consider for the calculation of this shear force. Okay. So I will just put all the values over here. See now, shear force VU. So VU is equal to sigma. What was the value of sigma we have calculated? Let me know the value. That value is not here with me. Let me know the value of soil pressure that we have calculated initially. 198.41. Ultimate. It is ultimate soil pressure. Do we have multiplied this soil pressure by 1.5? I want ultimate soil pressure. Please check it. 297.67. Okay. Always use the ultimate values. So it is, the answer is 297.67. Okay. So it is 297.67. This is our sigma into. Now hatched area. Now we want this much of area, which is hatched area. So what we will do, we will consider this whole area of the footing. So now what is the whole area? You know that this dimension is how much? It is 2.75 meter. This dimension is also 2.75 meter. Okay. So from this whole area, of footing, we will minus this much of area, because this much will contribute in the punching. So we will minus this much of area. So what is the dimension of that? So this length, you know, it is 0.5 plus d on both the sides. Okay, so what we will do now, I will write here, it is 2.75 into 2.75. This is my total area minus, I will minus this area which is going to be punched. So it is minus 0.5 plus d into 0.5 plus d. Okay, so here one more bracket we need to put, and now I will put here big bracket. So this is our equation in terms of d. Now if you solve this equation, then it will be Vu is equal to, so solve this now, multiply this 2.75.67 to 97.67 inside this bracket, and we will get one equation in terms of d. In terms of effective depth, we will get one equation. So how much it is? So if I write over here, it is 297.67 into, here in the bracket, multiplied by 2.75 into 2.75. How much it is? This is near about 7.56. Okay. Then this minus sign is as it is. Now you need to solve this. Okay. So first of all, zero point 0.5 into zero point 0.5, it is 0.25. So in it is minus 0.25. Then here 0.5 into d. Okay, so here it is again minus 0.5d. Then again d into zero point 0.5, and here the minus sign is there, so it is again minus 0.5d. And d into d square, minus sign is there, so minus d square. So why I have changed the sign of uh, all the quantities? Because here outside the bracket minus sign is there. So now ultimately what you will get, so Vu is equal to 297.67 into, here it is 7.56 minus 0.25 minus, it is d, minus d, minus d square. Okay, so now do the calculation and multiply this inside terms by 297.67. So if you multiply, then Vu is equal to, so it is, I will do the calculation with you, 297.67. First of all, how much it is? 7.56 minus, see this term, 7.56 minus 0.25, minus 0.25, so it will become 7.31. So 7.31 multiplied by 297.67, so it is multiplied by 297.67, so it will become 2175.96. Okay, so I will write over here 2175.96. This is our first term. Then what is the second term? Here it is minus d, so minus 297.67, minus 297.67d. Then again what is our third term? Again minus d square into 297.67, so it is minus 297.67 d square. This is our equation number 1. This is our equation number 1. Okay, so now this is the total shear force. Okay, this is the total shear force. Now from this total shear force, some of the shear force is resisted by the concrete. Okay, so if we want to avoid to provide the shear reinforcement, see, we have already studied this shear reinforcement in detail while designing the beams in DCS 1. Now just I am revising this. If we want to avoid the shear reinforcement means what? Placing of stirrups. So generally we don't place the stirrups in footing and in slabs. Okay, so now in footing we want to avoid the placing of stirrups. So we want that our footing is, we should provide a depth to the footing in such a way that the concrete which is present in the footing should resist all the shear stress or shear force. Okay, if the concrete alone resists all the shear force, then there is no need to provide the shear reinforcement. Are you getting my point? So now the next thing is we will calculate what is the shear resisted by concrete. So our next point is shear resisted by concrete. So this is the total shear. Now out of which shear resisted by concrete. How do we calculate the shear resisted by concrete? This we have already studied. Okay. So shear resisted by concrete. So we know the formula. VUC is the notation for shear resisted by concrete. Again the basic formula is same. Force is equal to stress into area. So it is tau C, that is permissible stress in concrete, into area is BD. Tau C BD. Okay. Now here is one concept you need to understand. What is the punching area? Okay. Now here, what is the punching area? So I will draw here. So now suppose this is our footing. What is the punching area for concrete that we want to know? How much area should be resisted by the concrete? Okay. And on this side, dotted line. Okay. Now this is our footing. Now see, this is the critical section. Okay. What I have drawn over here. So now pay attention over here. This is the section 0.5 plus D. हा जो पंच होणारा section आहे, this section will get penetrate through the footing. So I have drawn the 3D diagram of this section. Okay, to know the punching area, to know the width. So here, so as you know that this length, this is this length is how much it is? This is 0.5 plus D. Already we have derived. This is 0.5 plus D for the critical section. Then this is your depth. This is the depth. Okay. Now what is the area which is resisted to resist the shear force? Now that area I will show by hatching. So that area is this much of area. Whatever I am showing in hatching. This is your punching area. This area will punch. Okay. So this area is your punching area. Similarly on the other two surfaces also. This area is your punching area. So I will write here. So your punching area is punching area, and it is this much. 1, then 2. Okay, this is third, and this is fourth. This is your punching area. Okay. Now if I talk about the single area, so now we will let us do calculation over here, rough calculation sum. So if I talk about the single area, so how much it is? So see, this is the rectangle. This is the rectangle. It is 0.5 plus D, this dimension. Depth is D. So its area will be 0.5 plus D into D. This is the area. This is the area for single rectangle. This is the area for single rectangle. How many rectangles are there? How many rectangles are there? 1, then 2, 3 and 4. So if we want total area, we should multiply this by 4. So this is nothing but this is our punching area. This is our punching area where the during the punching action it will face some resistance. Okay. So now if I write over here this, so I will write VUC, shear resisted by concrete, is equal to, it is tau C, permissible stress. So what was the permissible stress we have calculated? The permissible stress is 1118 kilonewton per meter square. So I will take that 1118, okay, into what is my punching area? This whole area is the punching area, whatever written over here. This is the BD punching area. Okay, so it is 4 into 0.5 plus D into D into D. So now if you solve this equation again, what you will get? Now it is 1118 into 4. So how much it is? 1118 into 4. So it is 4472 multiplied by D. So 4472 D ने multiply करा आतल्या या bracket ला. काय मिळेल तुम्हाला? VUC is equal to 4472 D into 0.5 first term into 0.5. So it is 2236D. 2236D. Plus sign is there. So plus again 4472D into D. So it is 4472D square. So this is our equation number 2. This is our equation number 2. Okay. So now we will equate equation 1 and 2 so that we will get the value of depth. So equating equation 1 and 2. And now why we are equating equation 1 and 2? Because we want that whatever is the shear force generated, that all shear force should be resisted by the concrete. We don't want to provide the stirrups in the footing. That is why we want that whatever the shear force is produced in the footing, that should be resisted by the concrete. That is why we are equating this equation 1 and equation 2. So here what we will get, so I will write here in mathematical form, so that is VU must be equal to VUC. Whatever the shear force is developed, it is resisted by concrete. So now if you write both the equations and if you solve those equations, the equation are 21 2175.96 2175.96 minus it is 297.67D 297.67D minus 297.67D square, that must be equal to, 2236D 2236D plus 4472D square plus 4472D square. Okay, it is correct. So now solve this equation and let me know the value of D. Okay, ax square plus bx plus c, that form is there. So what will be your final equation? So now if you transfer this minus 297 this term, करा ह्या term ला पाठवा right side ला. Also send this term to right side. So what you will get ultimately? 4472 plus plus how much it is? 297.67. So it is 4769.67 d square. Okay. Again, this is 2236d, and transfer this term of d to the right hand side. Then 2236 plus it is 297.67. So it is 2533 plus 2533.67 d. Please do check the values. Values चुकून आहेत. ह्याला तिकडे पाठवल्यावर काय होणार? मायनस 2175.96. All this is equal to 0. Now this is the equation in the form of ax square plus bx plus c equal to 0. Now go to your calculator in equation mode and solve the equation. Okay, the degree of equation is 2. So two values over here. So first of all, the two roots x1 and x2. So I will write here two values are d is equal to 0.46. This is in meter, and d is equal to minus 0.99 meter. Okay. So as you know that, please check these values. Are you getting the same answer or what? I have solved it on the calculator and I have got this value. So now if you see over here, the depth, we are calculating the depth, and depth is never negative value. So we will add up the positive value, and the positive value is 0.46. Okay, and the positive value is 0.46. So here I will write, so therefore D required, what is the required depth for footing? The required depth for footing is 460 mm. That is your 0.46 meter is nothing but 460 mm. This is the required depth for the footing from two-way shear consideration. The required depth for footing from two-way shear, that is punching shear, two-way shear consideration is 460 mm. It is 460 mm. Okay. I hope now you are clear with this point. Okay. Any doubt in this? Anybody is having any doubt in this? What we have done? So if you are having a doubt, then only I will repeat once again what we have done in this punching shear calculation to evaluate the depth. Or if you understood, then we will move further. We will go for the depth calculation by one-way shear consideration. So again now I am asking if anybody is having any doubt in this. If you are not having any doubt, please reply me in the chat box so that we will move. So now I hope you understood this. So now we will move forward. So now next thing is depth calculation by, or we can write depth from, we can write depth from one-way shear consideration. One-way shear consideration. So now we will see one-way shear consideration. Okay. So now for the one-way shear, we know that where is our critical section? So for the one-way shear, our critical section is at a distance D. Okay, so now the critical section is at a distance D, you know that. So now I will directly draw the diagram so that it will be better for our understanding. How to take the strips? We will take two strips, one in X direction, another in Y direction, to evaluate the depth from one-way shear consideration. So now here, this is your column. So the dimension of the column, it is 0.5 by 0.5. You know that, zero point 5. This is the dimension of the column. Now I will draw the footing. So I will draw comparatively a large figure so that we can show the sections over here, strips. This is our footing. Okay, this is our footing. So now you know that the critical section is at a distance of D. So I will draw the critical section. So what we will do in the case of one-way shear, we will take critical section at a distance D. Okay, but we will take once along X direction and once along Y direction. In punching shear, what we do? In punching shear, we will take the critical section at a distance of D by 2 from all the four sides. Okay, but here in the one-way shear, we will consider the strips from two sides only. Okay, one strip is along the X, another is along Y. So how to do that? See over here. Now from this face of the column, okay, that is the vertical face of the column, I will draw the critical section at a distance D, which is somewhere here. Okay, so if you see, this is your critical section and this is your distance D. D is nothing but depth. Okay, so whatever I have drawn, this is your critical section at a distance D. So this critical section is along the, what we can say, the D is measured along the x-axis. Similarly, one more, so instead of taking right hand side, you can also take it on left hand side, there is no problem, but take it only at the one side, either at the left hand side or at the right hand side. Similarly, we will take one more strip which is either at the top or at the bottom. I am using the word which is either at the top or at the bottom. एक तरफ top लग गया, bottom लग गया. Okay, so now I will draw the line. So this is the next critical section. This is the critical section which we have considered at the top, and the distance from the face of the column, this distance is D. This distance is D. Okay. So now see here, we will evaluate the dimension. What is the dimension of this strip and all those things that we will calculate. Now see, we know that this footing, this total width is this total dimension, it is 2.75. Okay, this is 2.75 meter. So we always provide footing in such a way that the CG of the footing is matches with the CG of the column in the case of isolated footing. Okay, in the case of isolated footing. So here, this is the center point. Somewhere here, this is the center point. Okay, this is the center point. So now if this total is 2.75, now if I want to calculate half of this distance from the center up to this side, what will be the distance now? So it will be half of this 2.75. So it is 2.75 divided by 2. So it is 1.375. Okay. So this total distance, it is 1.375 meter. Okay, 1.375 meter. Now see, this total is zero point 0.5 for this column, This total is 0.5. So what is half of that? So now again if I take it for the column from the center to this point, this much, okay, so this distance is calculations of it. So this distance is 0.25. Okay, this is 0.25. Now this is D. So what will be this remaining distance? Now if I want to calculate this distance, see, from this point, from this point up to here, what is this total distance? What is this total distance? It is 1.375 minus 0.25. So we required all these distances, that is why we are calculating those. So it is 1.375 minus 0.25. So it is 1.125. So this distance is 1.125. 1.125. Now why we have done all these things? Because we want this area of the strip. Now if I show you the strip again, see this strip, we require the area of this strip which is at a critical section. Okay, so for that purpose we are doing all these things now. Now see, if I calculate this much of distance, what will be if I want to calculate only this much of distance? How much it is? How much it is? It will be, this total is, this total distance from the face of the column, it is 1.125. From the face of the column up to this point, it is D. So this remaining will be 1.125 minus D. So this distance will be 1.125 minus D for this strip. Okay. Now next is this distance. This is already known to you. This is 2.75 meters. That is already known to you. It is 2.75 meters. So this much is 2.75 meters. Okay. So similarly on this side also, now we will consider the same strip along this y-axis. So here, if you consider this now, you will come across the same distances as we have provided square footing and square column. If the footing is rectangular, now note the important point. If the footing is rectangular, then you should go for the strip or area which is having, which you should go for the strip which is having maximum area. Okay. So now here our footing is rectangular footing, sorry, square footing. So there is no question of plus and minus over here. So this distance, this is again, it is D, here it is minus 5 to 1.1. Okay, 1.125 minus D. So I will write clearly, is 1.125 minus D. Okay, so this is the distance. So if you see area of the both strips, it is same. So I will write that statement over here. So as as both the strips both the strips are are having are having equal area equal area, that is, what is the area of the strip? It is now rectangle, so 2.75 into 1.125 minus d. This is the area. Okay, just wait for 1 minute. As both the strips are having equal area, that is to see, if you see the area of the strip, so this is the rectangular strip, so this dimension is 2.75, and this much of dimension, this much of dimension, it is 1.125 minus d. This is the area of this strip. Similarly, if you consider for this strip also, this dimension is 2.75 and this is 1.125 minus d that we have evaluated. Okay, similar calculations what we have done here, you can do on this side also, you will get the same answer. Okay, so now the shear force we will calculate on this strip. So the simple formula is there. On this strip, whatever may be the shear force is acting, that we will calculate. So force is equal to, again they are basic formula, force is equal to stress into area. Okay, force is equal to stress into area, so that we will consider over here. So now if I write, so here as it is same, we can consider, I will write further, we can consider any strip. तुम्ही दोन्ही पैकी कुठलीही स्ट्रिप घेऊ शकताय, कारण त्यांचा एरिया काय सेम आहे. इफ द एरिया ऑफ बोथ द स्ट्रिप्स इज नॉट सेम, then you need to take the strip which is having greater area. Okay, so that you should remember, in case of rectangular footing it may happen. So now shear force, how to calculate the shear force now? So shear force is equal to, again our basic formula is same, stress or pressure, soil stress or soil pressure into area. So here your shear force Vu is equal to sigma. Okay, so I will directly write the values now instead of writing the notation. You know the notations now. So the sigma, value of sigma, what we have calculated, 297.67 into area. What is the area of the strip? It is 2.75 into 1.125 minus d. This is the area of the strip. Okay, so again do the multiplication, so that we will get the shear force acting on the strip. Okay. So now we are calculating the shear force which is acting on the strip. See, I will hatch this portion. Suppose now think about this strip. So on this area, whatever is the shear force is acting, this we are. So now here your shear force is. So we will do the calculations simultaneously. So now it is 297.67 multiplied by 2.75, it is 818.59. See, while doing the calculation of one way shear, you should consider either one strip of these two. एक स्ट्रिप आपण काय करतो, एक्स डायरेक्शन ला घेतो, एक स्ट्रिप आपण वाय डायरेक्शन ला घेतो. आय हॅव गॉट वन क्वेश्चन इज व्हेरी गुड क्वेश्चन. There are two strips. Okay, there are two strips. Then while considering the area of the strip, you should multiply the area by 2. Why we should multiply? Because there are two strips. This is the logical question is asked. Now see what is the answer of this question. See, we have considered one strip in x direction, one strip in y direction. Okay, but while doing the calculation, we will consider only one strip which is having greater area. Underline my words, we will consider one strip, double underline this, one strip, and next statement is which is having greater area, again double underline the word greater area. Now if you see in both in these strips, your area is same, so there is no question of greater area. So and out of these two we need to choose the one strip, so that is why we have taken the one strip. So whatever may be the depth we are getting over here on the one strip, same depth we are going to provide at the another strip. So there you should understand the failure pattern. Why this question comes into your mind now? See, at a distance of d, here your critical section is there. Okay, so from this point this footing will fail. ओके, म्हणजे इथनं हा क्रॅक जाणार आणि इथून याचे काय होणार आहेत, दोन तुकडे होणार आहेत. Okay, so this will part become a separate part and this strip will become a separate part. So it may fall along this critical section or it may fail along this critical section. So along which critical section it may likely to fall? The strip which is having a greater area, on that section this footing will fall or fail. Okay, but you can write down this statement. This is the important note. While calculating the depth from one-way shear, consider only one strip which is having greater area. Okay, so now moving further. So here if you multiply this 297.67 by 2.75, this will become one term multiplied by into 1.125. So it is, on my calculator the value is 920.91. Okay, you also check the value 920.91. Then here it is the minus sign in the bracket, so minus, again we will do the multiplication, 297.67 into 2.75 into D. Okay, so it is minus 818.59 D. So this is our equation number 3. This is our equation number 3 in terms of one-way shear, in terms of D, while calculating the one-way shear. Okay, so now this is the shear force which is developed in this footing due to one-way shear. Now we will calculate the shear resisted by the concrete. So shear resisted by the concrete. So how do we calculate the shear resisted by the concrete? VUC is equal to tau CPD. This is our formula. Okay. So I will draw this diagram for your understanding. I will draw this strip over here in 3D. Okay. So this strip is there. I will draw this strip now so that you will understand how the punching is happening, how the punching action is taken. Now this is our strip. Okay. So what area we have considered now, right now? This top area. So I will give the dimensions. So this much. How much it is? It is 1.125 minus D. Next is this dimension up to here. So how much is this dimension? It is 2.75 meter. Okay. Then next one is this one. This is how much? This is the depth D. So now what is the area of the failure? Okay. So shear resisted by the concrete. So concrete will resist this shear through which area? So I will hatch that area first so that you will understand. So that area is this much. This is the area. Where the shearing action takes place. Okay, where the shearing action takes place. So this is the area which is to be resisted. Okay, so what is the value of this area? So this area, if I want to calculate, A is equal to, so this dimension is 2.75 and multiplied by D. So this is the area 2.75 into D. So now VUC, shear resisted by concrete, is equal to tau C. What is the value of tau C? 1118 into area, that is BD, B is 2.75, D is as it is 2.75 D. So this is your equation number 4. This is your equation number 4. Now equate equation 3 and 4. Okay. So equating equation 3 and 4. Why we are equating equation 3 and 4? But because we want that whatever shear is developed, that should be resisted by concrete only. So if we equate this, then the equation is 920.96 minus 818.59D 818.59D, which must be equal to 1118 into 2.75 into D. Okay, so if you do the calculation, you can solve this equation. So I will do the calculation now. So it is 1118 into 2.75. This value works out to be 3074.5. Okay, so it is 3074.5 D. So multiplication of these two is 3074.5 D as it is. Now this term of D, if you shift to right hand side, then this will become plus. So I will add 818.59 in this 818.59. So the total term is 3893.09. Okay, so the total is 3893.09. So I will write over here. So this will become 3893.09D, and on this side this 920.96 will remain as it is. Therefore D is equal to, so it is 920.96 divided by our answer. So it is D is equal to 0.236 meter. Okay, 0.236 meter. So we can round up, we can say that this value is 236 mm. So therefore we can say that our D is, how much is our D? So we can round up this value to 240 mm. Okay, we can round up this value to 240 mm. Roll number 53, switch off your mic. So D is equal to 240 mm. Okay, so this is the depth from one way shear consideration. This is the depth from one way shear consideration. Okay, so now we have got two values. First is 460 mm and second is 460 mm from which, from punching shear criteria, and now from one way shear criteria we got the depth of 240. Okay, so now we will adopt the maximum depth. We will adopt the maximum depth. So what is the maximum depth now? Therefore here I will write provide provide maximum depth, provide maximum depth that is that is D is equal to 460 mm. This is the maximum depth. Okay, now generally for the footing we assume the clear cover of 50 mm 50, and we consider the minimum bar diameter as 16 mm bar diameter. Okay, because the footing carries heavy loads. For slab we go for 10 mm dia bars. For footing normally the minimum bar diameter, it is not a rule, but on site it is in practice that for footing we go for 16 mm bar diameter normally. So I will write over here assuming clear cover clear cover is equal to 50 mm, 50 mm and 16 mm dia bars, 16 mm bar diameter. Okay. So now we will calculate the overall depth and we will round up the overall depth. From overall depth again we will take the effective depth. So here overall depth capital D is equal to your effective depth 460 plus your clear cover plus half of bar diameter, half of bar diameter. So what is the answer? Do the calculation. 50 plus 16 by 2 means 8. It is 58. 58 plus 60. 60 plus 60 120. 120 minus 2 means 118 and 4. So it is near about 518. 518 mm. So we will round up this depth to 520 mm. Okay. So overall depth is 520 mm. So we are using capital D as a 520 mm. So if you increase the overall depth, then there will be increase in effective depth also. So therefore, again we will calculate the effective depth which is provided. Effective depth which we are going to provide. It is 520 is your overall depth minus, now reverse calculation, clear cover minus half of bar diameter. सो हे 2 ने वाढलंय म्हणजे हे पण काय होणार 2 ने वाढणार. सो इट इज 462 mm. It is 462 mm. So this depth we are going to provide. So we have decided the dimension of our footing. The depth of the footing is, its overall depth is 520 mm and its effective depth is 462 mm. This is for the footing what we have provided. Okay. So the next point it comes that bending moment calculation. So the next point is, after the evaluation of depth, now we will calculate the bending moment, then we will take the check for depth and then we will provide the steel. Okay. Now for the bending moment, this is the important point, you note it down. So for bending moment, critical section is taken at the face of column, at the face of the column. So underline this. Where do we take the critical section? It is taken at the face of the column. Okay. So along the x-axis we will take one section at the face of the column. Along y-axis we will take another section along the face of the column. Then we will calculate the bending moment in x direction and bending moment in y direction. Okay. So after that, whatever may be the maximum bending moment out of these two in x and y direction, for that maximum bending moment we will take the check for depth. Okay, and for each of the bending moment then we will provide the steel in x direction and steel in y direction. So that will be our last step. So now here I will draw the diagram again. So they told us that the critical section is at the face of the column. Okay, the section along x-axis I will draw first. The section along x-axis, that is the critical section. This line is not perfectly horizontal, but you can understand. So this is our section XX. Okay, this is the face of the column. Okay. You can also take the same section. हा section तुम्ही top ला घ्यायच्या ऐवजी इथे bottom ला पण घेऊ शकता. In that case, you need to consider the action from here. Okay. So section will be taken at the face of the column because this portion will behave as a cantilever. Okay. So here we have taken the section. So instead of this, you can also take the section at this bottom. पण एकच section घ्या, एक तर top ला घ्या किंवा bottom ला घ्या. Now the second section along y-axis. This is your section along y-axis, y. Section y. Okay. So now, if I write the dimensions, this is 0.5 meter. This is 0.5 meter. This total 2.75 meter. This total is also 2.75. Okay. So now, what is this much of distance? If I want this distance, how much it is? We have already calculated this distance. So see, this is the CG. So this is 2.75 is the total distance. This total distance is 2.75. So from the center up to this point, this distance will be 2.75 by 2. Again, this total distance is 0.5. So from center up to this point, this distance will be 0.5 by 2. So from this distance, if you subtract this one, then you will get this remaining. So if we want to calculate the distance, then it is 2.75 by 2 minus 0.5 by 2. So it is 1.125. That is, we have already calculated this. 1.125 meter. Similarly, on this side also, this distance it is 1.125 meter. Okay. So now, bending moment. What is the formula for bending moment? So for in the footing, the formula for bending moment is equal to WL square by WL square by. Okay. So what we need to do now? We know the value of L. Okay. We know 2 is the constant. We need to find out the value of W. Okay. We need to find out the value of W. Now I hope you understand this figure. Okay. If you haven't drawn it, then draw it quickly. So here it is column. This is the footing. 0.5 by 0.5 is the dimension of column. 2.75 by 2.75 is the dimension of the footing. So the center of column and center of footing are coinciding with each other. So if this total is 0.5, so from center to this point it is 0.25. From center to left hand side face of the column it is 0.25. And if this total is 2.75, then from the center up to the right hand edge of the footing it is 2.75 by 2. Okay. So in that way we have calculated this much of the distance and this much of the distance. Consider y direction first. Okay, you can go for x also. Y direction. Now I will draw the diagram of y direction. See, here your column is there. This is your column. I will write here. This is column. Then your section is somewhere here. This is the section. Okay. This is your section YY. This is your section YY. I am talking about this area. here, this area I am talking about. So now if you see how much is the distance remained, see this is the critical section YY. Here your column is there, that column we have shown here. This is critical section YY we have shown here. So how much is the distance remained to this side? This is the strip. It is 1.125. Okay, so that I will draw. Here it is. This is how much. This distance is 1.125. Okay, and how much is this distance? This total, this is 2.75. Okay, now we know the intensity of the load. Okay, we know the intensity of the soil pressure. What is the intensity of the soil pressure? Sigma. What is the intensity of the soil pressure? Sigma. It is 297.67 kilonewton per meter square. This is the intensity. Now we need to convert this intensity into the load. That is, we need to convert this into kilonewton per meter, so that we will get the load. Now we want to calculate the bending moment about this y section, about the y axis. So the bending moment is calculated about the y axis. To calculate the bending moment about the y axis, we must calculate the UDL along this. What is the UDL acting over here, that we should calculate first. What is the UDL? Okay, what is the UDL? And this creates moment about which axis? This creates moment about this y section, this UDL. Okay, so I will give the notation to this UDL. Say it is WY, because it is creating the moment about this y section. That is why I have used this notation WY. Now see the simple logic. Simple logic is there now. Suppose this is my area. Okay, and here my this dimension is 1.125 and this dimension is 2.75, and I know that on this area a stress intensity is acting, which is having a magnitude of 297.67. So this is in meter, this is also in meter, and this intensity is kilonewton per meter square. Okay, so now right now this is the intensity. So if I want UDL on this side, if I want to calculate the UDL on this side, so what is the unit of UDL? The unit of UDL is kilonewton per meter. Okay, so how do we convert this kilonewton per meter square into the kilonewton per meter? See, intensity is in kilonewton per meter square. If we multiply this by the meter, then ultimately we will get our answer in kilonewton per meter. So multiplication by meter means what? We need to multiply this intensity by one of the dimension. Which dimension, that we will decide later on. Either we should multiply by this dimension or by this dimension. Okay, is it clear to you which dimension? So now if we want the UDL on this side, so it is kilonewton per meter. So what is the total length? 1.125. So if we want the UDL on this side, then we should multiply by the opposite length. ज्या length वरती UDL पाहिजे त्याच्या opposite length ने multiply करा. So now see, we want UDL on this length. Okay, we want UDL on this length. So multiply the stress intensity by the opposite length. The opposite length is 2.75. So now if I multiply this by 2.75 meter, then I will get the UDL over here. This UDL I will get. And similarly, if I want to calculate the UDL on this side, what is the UDL? Then या साइड वरती UDL काढायचं तर opposite length काय? The opposite length is 1.125. So I will multiply this intensity by 1.125. So now in short, if I want to calculate the UDL, see here, this is creating a moment about y-axis. That is why I have used the notation WY. So I can write here WY. This WY, it is in kilonewton per meter, which is equal to what is our stress intensity? 297.67. This is our stress intensity. This is in kilonewton per meter square. Okay, multiply by now we want UDL along this x-axis so that it can create the moment about y-axis or this y section. So ह्याला पॅरलल लेंथ कुठली आहे त्याला सोडून द्यायचं. ही लेंथ कशी आहे हॉरिझॉन्टल. वी वांट UDL along x-axis. We want UDL along x. So we need to multiply by the y distance. So the y distance is 2.75. ह्याच्या अलॉंग UDL पाहिजे ना तर ह्याला पॅरलल असलेली ही लेंथ आहे ह्याला सोडून द्यायचं. राहिलेल्या लेंथने मल्टिप्लाय करायचं. ओके. So what is the remaining length? It is 2.75. 2.75. This is in meter. So if you multiply this, you will get the UDL. And what is the value of that UDL? It is 297.67 multiplied by 2.75. So this is the UDL. It is 818.59. 818.59 kilonewton per meter. Kilonewton per meter. This is the intensity of UDL which we got. Kilonewton per meter. Okay. Now what is this length? This length we already know it is 1.125 meter. So if we calculate the bending moment, then the bending moment is bending moment in y direction. So we know that here bending moment in y direction is equal to Wy into Ly square divided by 2, Wl square by 2. So here I will write this intensity 818.59 into on which length it is acting, Wl square by 2. The length is 1.125. It is 1.125 square Wl square divided by 2. So now if we solve this, it is Wl square. So you will get the value 518.01. Okay, this is your bending moment. So it is 518.01 kilonewton meter. So this is your bending moment in y direction. This is your bending moment in y direction. This is your ultimate bending moment. Okay, because we have considered the ultimate intensity. Now similarly, we will calculate the bending moment along x direction. So to calculate the bending moment along x direction, okay, so here I will write bending moment in x direction. Okay, so how to calculate the bending moment in x direction? Again, we will draw the same diagram. This is your column. I will draw over here. So this is the column. So column, then your section is along x. So this is the line. This is x-axis, section along x-axis, and here is this much of distance. Now we want to calculate the UDL, and again the same thing is there. We want to calculate the UDL over here. Okay, and this UDL is this may be acting like this, and this UDL will generate the moment along this x-axis. So it is generating the moment along x-axis. So let it be. I will call this UDL as WX. WX. So the lengths are already known to me. So this is the length. How much it is? 1.125 meter, and this above length is 2.75 meter. Now we want to calculate the intensity of UDL. So it is Wx is equal to, what is the intensity? So Wx, which is again in kilonewton per meter, which is equal to intensity, it is 297.67. This unit is kilonewton per meter square multiplied by, आता बघा, I will explain in Marathi so that you can understood. मला UDL कुठल्या लेंथ वरती पाहिजे? या लेंथ वरती पाहिजे, म्हणजे या डायमेन्शन वरती, या लेंथ वरती UDL पाहिजे. सो ही लेंथ किती आहे? याच लेंथ वरती असा UDL काय पाहिजे? हाच UDL तुम्ही इथं पण दाखवू शकताय किंवा हाच UDL तुम्ही इथं पण दाखवू शकताय, नो प्रॉब्लेम. याच लेंथ वरती मला UDL का पाहिजे? कारण इथं जर UDL असला तरच तो अबाउट एक्स ऍक्सिस मुवमेंट देणार आहे. समजतंय का? जर तुम्ही UDL असा घेतला तर इट विल गिव्ह यू द मोमेंट अबाउट झेड ऍक्सिस. Okay, use right hand thumb rule for the direction of the moment. So now here UDL is there, so it will produce the moment along this direction. So ही लेंथ किती आहे? 1.125 मीटर ही लेंथ. मग मला इथंच UDL पाहिजे, तर ही लेंथ द्यायची सोडून, ह्याला पॅरल असलेली लेंथ म्हणजे कुठली? 1.125 दिली सोडून, राहिली कुठली लेंथ? ही राहील. लक्षात येते काय सांगतोय ते? So it is 2.75. So multiply this by 2.75. So this is in meter. So you will get the intensity of the UDL. So how much is the intensity of the UDL? 297.67 into 2.75. It is again 818.59 kilonewton per meter. This is square footing, that is why the intensity is constant. In case of rectangular footing, you may get the different intensity. Okay. So in the similar manner, now we will calculate the bending moment. So bending moment along x direction, which is W. Now I will write directly W L square. What is L now? L is the span. So this is the UDL, and the span of the UDL is this one, 1.125. So it is 1.125 square divided by 2. Again we will get the same answer. So our answer is, how much it is? Bending moment आपण calculate केली तर वरच आहे, 518.01 kilonewton meter. Okay. So on the both the sides we got the same bending moment. That is bending moment in x direction 518.01, bending moment in y direction 518.01. Okay. Now after the calculation of both the bending moments, our next point is we will take the check for depth. So here check for depth. We will take the check for depth. Now for checking the depth, you know that equate the maximum bending moment to moment of resistance. To the moment of resistance. So what is our maximum bending moment? 518.01 into 10 to the power 6. It is in Newton mm, which is equal to, now M20 and Fe415 is there. For Fe415 it is 0.138. FCK is 20 into B. B is the dimension, another dimension, it is 2750 into D required square. Here don't put B is equal to 1000. Okay. कुठं सुद्धा आपण असा assumption केलेलं नाहीये की considering per meter width analysis किंवा assuming 1 meter width असं आपण या footing मध्ये कुठेही केलेलं नाहीये. ते 1 meter width आपण कुठे assume करतो in the case of slab. Okay, in the case of footing now it is 2750 is the width. So now calculate the D required from this. So D required is equal to, so please do the calculation. You also check the calculations. This 518.01 10 raised to 6 divided by 0.138 into 20 into 2750 square root of answer. So it is 261.18 1.18 mm. 261. It is 261.18 mm. Okay. So here D provided whatever we have, how much we have provided 462 is greater than D required. D required. Hence safe. Hence it is safe. Okay. Hence it is